Welcome to part 5 of our video series on estimation. In this video, we are going to return to the concept of pairing data, but we're going to talk specifically about why we pair data, okay? And then we're going to discuss the data setup that pair data takes in order to do statistical or inferential analysis with the data. I'm Renee Clark from the Swanson School of Engineering at the University of Pittsburgh. Okay, so let's talk about why we pair data. Okay, let's recall before and after studies that we discussed in a previous video, okay, in which the same person, or it could even be an item, is measured both before and after a certain intervention or method that you are trying or testing out, okay? Let's say that intervention happens to be a new teaching method in the classroom or something you're trying different in the classroom, okay? And you are trying to assess students' abilities with your enhanced or new method. Now with pairing, okay, you're able to test that same child's ability both before and after you apply your new method. Now, if you're able to do that, to test that same child's ability, both before and after, okay, that's better than, okay, testing your method using two completely independent groups of students that have different students in each, completely different students in each group, okay, in which you may test one group with your method and then compare that to a second group in which you didn't use your method, okay? Pairing is better than using two independent groups. And the reason for that is with pairing, okay, you're able to control for variables that exist between students, okay? Things such as perhaps what might have been their prior knowledge on a topic or in a certain area, or what their natural capabilities might be. It could also include variables such as, more social variables such as parental oversight or socioeconomic status, etc., right? There are many, many, many variables that lead to differences student to student, but with pairing, you're able to control for these variables, okay? So in essence, what pairing does, it eliminates or controls for these other sources of variability. That's key, okay? So you'll recall that with pairing, okay, the experimental unit remains the same both before and after, or without and with your intervention, right? So let's say we are measuring Renee. She is an experimental unit, but we're going to record her measurements both before and after, okay? Each row or each subject is an experimental unit, and they remain the same throughout the study, both before and after, okay? So this experimental unit remains the same or has the same variables both before and after, including variables that are not being tested, right? Okay, so mathematically, pairing reduces the variance, okay? It reduces the variance in the difference between your two variables. So X and Y represent your each of your two populations, dependent populations, okay? This is the formula for the variance of the difference in the two populations. And why mathematically the variance is reduced is because you are subtracting the positive covariance there. Okay, you can see how you're subtracting that. You're subtracting 2 times that, but the covariance term is positive, okay? And so just recall that covariance is a measure of the nature of the linear relationship between two variables. In this case, the two variables would be X and y. And these variables are not independent, right? They're dependent because they're paired. So if they're dependent and not independent, you would expect them to have a relationship of some sort. Okay, so with paired data, it has a certain setup in order for statistical analysis. Okay, so with paired data, we say that we have n rows, subjects, or pairs, however you want to say it. Okay, so in this example shown here, we have 6 rows or 6 pairs of before and after data. X1 represents the before measurement, X2 represents the after measurement, okay? And if you recall from an earlier video, the quantity that we're actually going to be analyzing with a paired data analysis is the difference between the two measurements, okay? And we call these differences between the x1 and the x2 d sub I, where I is just simply the subscript on the row number, okay? But the difference is calculated either by taking x1 minus x2 or x2 minus x1. It doesn't matter in which order you take the difference, okay? So for the first row, for example, you see that its di, or its difference, is equal to 1, which was obtained by 2 minus 1. So we took x2 minus x1. Second row, value of 2 was 5 minus 3, and so on down the table, okay? So with this data, we obtained 6 individual differences, right? Because there were 6 rows. Okay, so what you do next with these differences is that you average them. Okay, so it just so happens that these differences happen to be equal to 1, 2, 3, 4, 5, 6. But if you were to take the average of those 6 numbers, you would calculate 3.5, which you can see is right in the middle there. We call that average D bar. Okay, so it is D bar is considered the average across all your individual differences in that table. Okay, using those 6 individual differences, 1, 2, 3, 4, 5, 6, we also calculate the standard deviation, which again, if you were to calculate the standard deviation of 1, 2, 3, 4, 5, 6, you would come up with 1.9. We give that the symbol S sub D for standard deviation of the differences, okay? But what S sub D is, it is the standard deviation for all of your individual differences, DIs. Okay. We wish to thank the National Science Foundation under Grant 233-5802 for supporting our work. Thank you for watching.